recording is on, and I'm again recording this my main screen, the same one that you are seeing. So if you are chatting, then those chats don't show up, so your name does not appear on the screen. Last time we had the circuit analysis of DC circuits, and today's topic is about AC circuits, and especially one very practical thing is filters, mostly analog filters. You will be also doing very simple digital filter on the exercise on the afternoon with Juho. Or actually that is actually a exercise. Okay. Typical yada yada. Couple of words about the AC circuits, what they are. So AC stands for alternating current, and in general electronics are AC circuits. And basically what you need to now get some information or some knowledge is how the time-based signal analysis goes. What happens to the signal when you have a real system, so to speak? So practically, we already covered most of the stuff on the DC part. Fundamentally, the laws that we discussed already, they are the same. And the main differences are basically those couple of bullet points there. So in addition to resistance, we also have complex impedance, or actually it's called reactance. And that basically, if you have an impedance, if you have a capacitor, then the impedance is marked usually Z of C, and then inductor, then it's Z of L. And practically these three components, resistor, capacitor, and inductor, can be used to design any linear circuit in electronics. Linear meaning that basically the superposition principle works, and it's okay. Let's not go into that. It's more about the philosophy. And another one, in addition to those extra components, we also have signals. Can be thought that they are signal is varying by time, so it could be periodic, sinus minus sinusoid. It could be sum of harmonic periodic signals. For example, a square wave can be broken into sinusoids, the harmonic sinusoids. Then we have step functions. So step function, actually it's more or less like turning something on or off, meaning digital. And then we also have the arbitrary signal, like on a system's point of view, speech or music, that's arbitrary random signal. Okay, and again, basic elements in AC, in addition to resistors and voltage current sources and the connectors, that kind of things, we have capacitors. Different type of capacitors, basically ceramic ones that start from 1.5 picofarads roughly up to 1 microfarad. Okay, so thinking of the range of the capacitors, that's actually pico is 10 to minus 15. Microfarad is 10 to minus 6. So that's the range of the sizes, capacitor sizes, range from 10 to minus 15 to 10 to minus 3 or something like that. So it's 12 decades of different value capacitors for different uses. And as a curiosity, the capacitor can also be variable kind. So you can turn and the high tune a capacitor just what you want to be. This I used in, for example, radio frequency tuning circuits. Another AC element is an inductor, which is simply a wire coil or coil made of a conductive wire or thin film, which is also a wire. And it could be either on air core, meaning that there is some plastic or something like that you are winding this wire around it, or ferrite core. And again, there's a quite not that huge variety anymore. But anyway, so there's a big variety of different sizes and different types and for different applications. For this course, basically, we just use a general term inductor or general term capacitor. We don't care much about the what type it is. Although in real life, you need to, especially on the capacitors, you need to check the polarity of the capacitor, since the electrolytic capacitors actually can generate some serious amount of smoke or even burn if you accidentally switch the polarity. So some care must be taken, but that on the simulator you don't see the difference probably. Okay, so those elements. Then about the signal sources. Okay, for these a usual way of marking signal as variable of time is to use lowercase letters. And if there is a signal source, usually the signal source has this kind of the wave symbol inside of it. So that's basically a tilde character, which is showing a wave. So it's a wave source. Pretty simple. But still, you have only the output resistor inside of the Thevenin's model. It may have this variable, the voltage source, but the resistor is still a resistor at the output. It doesn't have the complex impedance. If a amplifier output or such happens to have some reactance, then it's marked usually outside of that model. Okay. Mathematics. Yes. This kind of circuit analysis stuff tend to be a bit math heavy. And here we are basically dealing with complex numbers, meaning in complex math is done in complex plane, which is a place where no magic happens. It's plain good old engineering. So you will be engineers. You should get used to also do mathematics in complex numbers. Because one reason, signal phase basically is quite important thing to understand, since the modern data transmission technology, for example, it's based on phase shift, not amplitude modulation anymore or not even a frequency modulation. It's phase shift modulation. PSK, phase shift keying. It's all about phase. So complex numbers needed. But anyways, it's called engineering. That's why you are here on the University of Applied Sciences to actually learn and practice these things. Okay, that was the overall view of what happens in the following next couple of hours. Impedance. I told already about the impedance that on resistive circuits, the resistance is called the impedance. Here on with the capacitor and inductor, we are calling impedance Z. However, for example, the Ohm's law, it's the same. The voltage drop across any element which has a impedance actually is proportional to the current and multiplied by the that impedance Z. Okay, that's the definition of Ohm's law, and it's still it's just the symbol is changing, nothing else. So nothing else. Just a moment. There's some. Okay, there were some problems. Okay, now I'm quite sure that I don't have any connection problems anymore. I get 100 megabits downlink and 50 megabits per second uplink. I'm actually on, as I said last week, I'm on a different place now. Much better connection. Okay, so back to the business. So U equals Z times I. And what the impedance can be. Resistors actually behave exactly the same way in both DC and AC circuits. So Ohm's law actually just is the same. U equals R times I if it's a resistor. Inductors. Okay, that has that coil, a wire coil. That actually transfers electric energy into magnetic field. You remember from the physics that basically if you have a current flowing through a loop, then it induces magnetic field at the center of that loop. So practically it transfers the electric energy into magnetic field, which actually slows down the current change rate. So basically the other way around, thinking of how this power generator works. It has a magnet, and then you rotate, basically change a magnet, the magnetic field through a wire loop, and you induce voltage across the that wire or that coil. The same thing here. But anyhow, if you have a small signal as such, then basically you can analyze all of those circuits using Ohm's law. Okay, U equals C times I by having the impedance of inductance, which is ZL, J times omega times L, where the L is the inductance. It's the value of the component. And okay, there's a marking. J is as marked as imaginary unit. Oh, that's the engineering way. I here, that's current. Okay, that's one of the reasons why in general the engineers prefer to use J as the imaginary unit compared to I, which is the mathematician's way. physicists actually, they use either or whatever, whatever fits the purpose. Okay, then the omega here is angular frequency, meaning it's such a shorter way of writing 2 times pi times f, where f is the physical frequency in hertz. Okay, so that way actually now we know, using the Ohm's law, we know exactly what is the voltage across an inductor if the current is sinusoid, for example, sinusoid, or the other way around. Anyhow, now we have a tool to do some serious the system analysis or signal analysis. The capacitance, it's the similar kind of component, although capacitors are working quite like batteries. When a battery is flat, a rechargeable battery, then you start charging it by a current. So current goes in and you start rising the battery voltage. Then basically when you're just drawing the current from the battery, basically the voltage drops. Okay, capacitor is exactly the same, but it's also linear kind of element. So basically the this constant current produces a constant rate rise of the voltage. Okay, so practically what happens here, capacitors charged by current flow, which slows down the voltage change rate. Okay, so there's the ZC, which is the impedance of capacitance, is 1 over J omega C. Nothing magic here. Again, C is the capacitance of the capacitor, and then J omega is the imaginary unit times angular frequency. And we have again a nice tool to analyze any AC circuit. How about the Kirchhoff's laws? Well, they are actually quite obvious, because this actually comes from the physics. Current doesn't go anywhere. So if you have a current junction, the incoming current is the same as the sum of the outgoing currents. So if you have a current junction, like in here, the red plot, then basically you have the incoming currents the same as the outgoing currents, the sum of them. The second law, the voltage law, states that the directed sum of the voltage potentials around any closed loop is zero. So yes, it's the same thing again. So practically the voltage across Z1 plus voltage across Z2, is still the same as this voltage source here. So the voltage does not generate itself for no reason. Okay, so exactly the same analysis rules. And let's take a AC review on this circuit analysis shortcuts. So the equivalent impedance, meaning series impedances, we have two impedances Z1 and Z2. We still have the same stuff and the same mathematics, and we can actually replace that one by an impedance with the sum of Z1 and Z2. Okay, in series, you just add the impedances. And there you have the imaginary unit sometimes involved. That's not a big deal. There are plenty of different the math tools that you can actually use to calculate the complex numbers. And when pen and paper is still a valid method. Then that same circuit again, it's still a voltage divider. So U1 equals that the current times Z1, and the current is actually U divided by Z1 plus Z2, the total impedance. So practically we have the same the equations as in with the resistors, but now we just have these complex impedances replacing the R, the resistance. And then let's take an example, RC circuit, meaning that it's a resistor and capacitor in series. So we have the signal input on left and signal output on right. So basically this is the one marking that we are referencing on a common ground, and that's the total voltage. So basically total voltage here is that U, and then we are looking at U out, which is now the voltage across impedance Z2. There. So the voltage across Z2, which is U2. And we have this equation, voltage divider equation. And remembering that, okay, impedance of resistor is R and impedance of capacitor is that 1 over J omega C. And using the previous voltage divider equation, we get a little bit nasty looking formula here, which is actually quite simple at the end. So we have the input signal times 1 divided by 1 plus J omega RC. Interesting. So what does this actually do? So we will actually revisit this one later. So it looks like we have a circuit that depends on the output depends on the signal. Whoops, where did it go? Oh, sorry. Signal frequency omega and also the R and C. So the signal frequency we usually cannot do much about, so it's what it is. Especially if this was an input from a sensor. But those R and C values we can select, so we can change the behavior of this circuit by selecting components R and C. Okay, just as for the symmetry's sake, then we have this also equivalent impedance for the parallel circuits. So the same thing, two impedances in parallel. There we actually have the current junction and the same voltages, and it actually brings us this formula that the conductance or 1 over the impedance is equal to the 1 over Z1 plus 1 over Z2, and there's a formula for that one too. Okay, so that's equivalent to that impedance. Or this works also as a current divider. Not a biggie. Totally symmetrical with the these DC parts. And this is just a curiosity. I'm not asking you to do analysis of this sort of things, not too many times actually. So on the exercise, you will actually do a quite practical, uh, quite practical calculations. But anyways, that'll be later. So this is just to show you that, okay, we have done it with the resistance, with the same way, exactly the same way. If I put this next to our resistance resistor example, it's exactly the same. Only the impedances change from R to Z. And this is very generic form. And of course, at the end, you could show this basically a little bit nicer looking. So these are ugly. Your math teacher would actually hate me for showing this kind of ugly equations. But this is not mathematics, this is engineering. Okay, so let's wrap it up again. What was different in AC compared to DC? So resistance, in addition to resistance, we also have the complex impedances for capacitor and inductor. Both of them vary by the signal frequency, and then also the signal is varying by time. So usually periodic or step kind of signals. We are not going to analyze much of these step kind of signals, since that then the mathematics gets a little bit ugly. Basic elements, capacitor, inductor, they are different type of both of them. Capacitors from different material, which is the electrolyte or this material between these plates. So the simplest capacitor is just two metallic plates next to each other, not touching, but there is an insulator in between. And then depending on what are the electric properties of the insulator, the capacitance actually can be controlled. Inductor, it's just a coil, and adjusting the material of the core, you can change the value or just wind more wire. Thevenin's model, same, except that it has this alternating voltage source. Impedances. On Ohm's law, the impedance is proportional to the current. What I'm saying, impedance is, the voltage is proportional to the current times the impedance. Okay, same, exactly the same as on the resistor. Then some talks about the impedance. Impedance of a resistor is same as the resistance. Inductors, the impedance is J omega L. So it's imaginary, okay, imaginary number. Well, that's because it actually changes the phase by 90 degrees. And so practically this one, what it means that the inductor actually delays signal 90 degrees angle. So if you have a sinusoid, then the current is, if you have a voltage across this inductor changing, then the current will follow 90 degrees later. Capacitor, the opposite way around. So basically, if I have a current flow through the component, then the voltage follows. So basically, it means that it has a negative delay. Mathematically, it looks like that current is actually is advancing 90 degrees compared to the voltage change. But anyways, it's just about the type. So plus 90 degrees and minus 90 degree phase angle changes. Nothing more than that. Kirchhoff follows the same shortcuts, still the same. Those series impedances or works as a voltage divider. Example, voltage divider between resistor and capacitor will actually end up being a circuit that looks like it's filtering something. So that part is fairly interesting. And then we have also the equivalent impedance for the parallel impedances, which work also as current divider. And although the math looks ugly, it's still the same as in the case of resistors. Okay. Now it might be actually, if you need to take a break, we might actually have a 3 minutes break right now. Since the next is quite important, I would like to spend a little bit more time. I don't want you to be too tired for that one. So let's have a 3 minutes break.